Curved mirrors. Last week we were talking about plane mirrors. A plane mirror is a flat mirror. Today we're going to look at a couple curved mirrors. I'm going to start with C, which is the center of a circle. I'm going to chop off the top and the bottom of the circle to make two different mirrors. There's an imaginary line that goes through the center of the mirror called the optical axis. This mirror on this side that curves inward is called a concave mirror. The one that curves outwards is called a convex mirror. In the middle between the center and the mirror is a point called the focus point. This is the focus point for the concave mirror. This is the focus point for a convex mirror. Now this distance from the focal point to the mirror is called the focal length. Our first mirror we'll look at is the convex mirror. It's also called a diverging mirror. This is the one that curves outward and it spreads light outward. Light rays that come in parallel bounce outwards in all directions like they're coming from that focus point that's behind the mirror. The image, let's take a look at the image here. This is a convex mirror and the image in here appears to be smaller. It's upright. And when we're describing images, I'm going to ask you to describe it with these three sets of words, either larger or smaller, upright or inverted, real or virtual. For the last one, virtual, we recognize virtual images because they are upright. We recognize real images because they are inverted. But that is not what the definition of these words are. I'll show the definition when we do the ray diagrams. For a convex mirror, the image is always smaller, always upright, always virtual. Pause and copy. This is a side view mirror of your car. This is a plane mirror. And this little portion up here is a curved mirror. This is a convex mirror. And this is the one that has a little warning at the bottom. It says objects are closer than they appear. And what's going on here is the object is smaller. This mirror makes things smaller, which is good because you get a wider field of view. But you also think that smaller things are going to be farther away from you. And this object is actually closer. It's the mirror that's making it smaller, not the distance. The other mirror is the concave mirror. For this one, the mirror curves inwards, and it takes all of these parallel light rays that come in and focus them into the focus point. Pause and copy. Let's look at the images here. This mirror can make several different types of images. The one on the left here is larger, it's upright, and because it's upright, I recognize that it's a virtual image. The one on the right side is smaller, it's upside down, and because it's upside down, I recognize that it's a real image. So for this mirror, it can make either images real or virtual. The virtual images will be larger and upright, like a magnifying glass. The real images can be inverted, and it can be either larger or smaller. Pause and copy. Light ray diagrams. We have a couple rules for light ray diagrams for each of the mirrors. We'll do the concave mirror rules first. Light coming in parallel to the optical axis reflects through the focus point. Light coming in through the focus point reflects parallel to the optical axis. Notice that these two rules are opposites of each other. That helps us remember them easily. Rule number 3, light rays coming into C reflect along the same path. Pause and copy. Let's look at an example here. This is a concave mirror. I've labeled the C, the center of the circle, and the focus point F. We'll put our object out here sitting on the optical axis. Now all of our light rays, we're going to have them come from the very tip of the object because we're trying to locate where the tip of the image is. So first light ray is going to come in parallel and bounce through the focus point. Second light ray is going to start at the same point, and I'm going to make it a different color so we don't get the light rays confused. This one goes in through the focus point and bounces out parallel to this optical axis. The third light ray is going to start at the same point again and go through C. When it bounces off the mirror, it bounces straight back along the same path. Notice there's a point here where all three of these light rays intersect. That intersection, we say that they converge, and this is why this mirror is called a converging mirror. This is also the reason and the definition of what a real image is. A real image is where the light rays converge in front of the mirror. There's a definition of what a real image is. So this is where my image is going to be. The light rays came from the tip of the pencil, so this is the tip of the pencil. The eraser of the pencil is on the optical axis, so this eraser is also on the optical axis, and you can see that's why this image is inverted. The other thing about real images is that we can project them onto a screen, and that means I can put a little card here and shine a picture of the pencil onto the card. Convex mirror rules. Light coming in parallel to the optical axis reflects as if it came from the focus point. Light coming into the optical axis reflects at the same angle. And rule number 3 is the same as the concave mirror. Light going into C reflects along the same path. Pause and copy. Let's look at an example. This is the convex mirror. It curves outwards. Notice that the focus point and the center of the mirror are on the back side of the mirror, and the mirror is on the front. So we're going to put our object out here in front. The light rays always have to come from the tip of the object, so the first light ray comes in parallel, and it goes out as if it's coming from this focus point. Second light ray comes into the optical axis. We're going to come right down here. It bounces back at the same angle. Last week we learned this is called the law of reflection. Angle of incidence equals the angle of reflection. Third light ray is going to come into point C, and when it hits that mirror, it bounces backwards. You can see here that these reflected light rays do not converge, and that's the definition of a virtual image. The light rays do not come together. It makes a virtual image. To locate where the image is, we're going to take these 3 reflected light rays and we're going to trace them backwards behind the mirror with dotted lines. And you can see that there's a point here where all of these extensions converge. This is where our image will be located. This is the tip of the pencil, and the eraser again is on the optical axis. So you can see that this image is upright and smaller and virtual because the image is actually behind the mirror. In the concave mirror, the image was in front of the mirror. That's what makes it real. All right, these are the formulas that we use for mirrors. It shows measuring the distance of the object and the image, how they're related to the focus point. For the magnification, there's 2 magnification formulas. It's the height of the image divided by the height of the object, or it's also the same ratio between the distance of the image and the distance of the object. The minus sign tells whether we're inverted or not. If you have a negative magnification, your image is going to be inverted. If it's a positive magnification, your image is going to be right side up, and that's why there's a negative sign in the formula to make that sign convention come out. So let's look at this ray diagram for the convex mirror. I pointed out that C and F are both behind the mirror, and that means that focus point, when you're using it in the formula, you have a negative number because it's behind the mirror. This virtual image is always going to be behind the mirror, and that means the DI is always going to be a negative number. DI is the distance along the optical axis from the center of the mirror to the image. DO is going to be along the optical axis from the center of the mirror to the object. For the concave mirror, this image is in front of the mirror, and that's why it's a real image. Our DO is going to be the distance from the pencil to the mirror. DI is the distance from the image to the mirror, and F is the distance from the focal point to the mirror. In this case, the F is always in front of the mirror, so F is always going to be positive. For both of our mirrors, our DO is always going to be positive. You always put something in front of the mirror. You're not going to put it behind the mirror. So I didn't write that one down just because it's common sense. All right, let's pause and copy.